Alright, so welcome back. This will be the last chapter for 207 as far as new material goes, and we'll wrap it up by talking about statistical inference. So, estimating a population parameter based on a sample statistic is one area that we call statistical inference. The basic tools for estimation were introduced in Chapter 8, the last video series, and another important application of statistical inference is hypothesis testing. So in hypothesis testing, a statement concerning a population parameter is made. We then use the sample data to either deny or confirm the validity of the proposed hypothesis. This sort of testing is performed regularly in many industries, such as pharmaceutical industry, where they will test the hypothesis on a new drug product before they are deemed to be safe and effective by the FDA. So in many of these instances, the drug is hypothesized to be both unsafe and ineffective. Here the FDA does not wish to certify that a drug is safe and effective unless there is sufficient evidence obtained to prove or support that it is safe. If the sample results from the studies performed provide significant evidence that the drug is safe and effective, then the FDA will move that on to market the drug. So hypothesis testing is a major part of business statistics, and Chapter 9 introduces the fundamentals involved in conducting a hypothesis test. Many of the remaining chapters in the text also introduce additional hypothesis testing techniques, so you need to gain a solid understanding of these concepts based on one population. So after this series, you'll be able to formulate a null alternative hypothesis for a single population mean and proportion. We'll cover type 1 and type 2 errors and formulate decision rules for testing the hypotheses. And then we'll also cover 3 approaches to test a hypothesis. And then we'll wrap up by actually computing the probability of a type 2 error. So by now you know that the information contained in the sample is subject to sampling error. The sample mean is almost certainly not equal to the population mean. Therefore, in many situations you need a test to claim about a population mean by using a sample mean. So you can't simply compare the sample mean to the claim and reject the claim if x bar and the claimed value of mu are different. So instead, you need a testing procedure that incorporates a potential for sampling error. Statistical hypothesis testing provides managers with a structured analytical method for making decisions of this type. It lets them make decisions in a way probability of decision errors can be controlled or at least measured. So even though statistical hypothesis testing does not eliminate the uncertainty in the managerial environment, the techniques involved often allow managers to identify and control the level of uncertainty. The techniques presented in this chapter also assume that data are selected using an appropriate statistical sampling process like we covered in earlier chapters, and that the data are interval or ratio level. In short, we assume that we're working with good data here. Otherwise, the entire test is a waste of time. In hypothesis testing, there are 2 hypotheses that are formulated. One is the null hypothesis. The null hypothesis contains an equality sign such as equals, less than or equal to, or greater than or equal. The second hypothesis is the alternative hypothesis, represented by H sub A. Based on the sample data, we either reject the null hypothesis or we do not reject the null hypothesis. In many cases, you'll be interested in whether a situation has changed. We refer to this as testing the status quo. And it's a common type of application of hypothesis testing. So for example, the Kellogg's company makes food products including a variety of breakfast cereals, and at the Michigan plant, Frosted Mini Wheats are produced and packaged for distribution around the world. So if the package process is working properly, the mean fill per box is 16 ounces. And every hour, a quality analyst at the plant selects a random sample of filled boxes and measures the contents. They do not wish to unnecessarily stop the packaging process, since it would be costly to do so. So the packaging process will not be stopped unless there is sufficient evidence that the average fill is different than 16 ounces. So the analysts use the sample data to test the following null and alternative hypothesis. The null hypothesis is reasonable because the line supervisor would assume that the process is operating correctly before starting the process, as long as the sample mean is reasonably close to 16 ounces. So only when the sample mean is seen to be too large or too small will they reject the null hypothesis and take action to identify and fix the problem. So in this case, the null is such that the mean is equal to 16, and the alternative is that the mean is not equal to 16 ounces. We might also have a scenario about a research hypothesis. So in this case, statistical evidence is needed to indicate that the new product is effective. The default position or null hypothesis is that it is no better than the original, or in the case of a drug, that it's unsafe and ineffective. So the burden of proof is placed on the new product, and the alternative hypothesis is formulated as the research hypothesis. So for example, Goodyear Tire and Rubber Company has a new tread design that its engineers claim will outlast its competitor's leading tire. So if Goodyear can be sure that the new tread design will last longer than the competitors, it will realize a profit that will justify the introduction of a tire with a new tread design. So the competitor's tire has been demonstrated to provide an average of 60,000 miles of use. So therefore our research hypothesis for Goodyear is that the tire will last longer than its competitors, meaning that the tire will last an average of more than 60,000 miles. Also pay attention to how the null and alternative hypotheses are written. So for consistency purposes, the rule adopted in this text is that the claim contains the equality, always. The claim becomes the null hypothesis, and if the claim does not contain an equality, the claim is the alternative hypothesis. So for example, a recent radio commercial stated the average waiting time at a medical clinic is less than 15 minutes. A claim like this can be tested using the hypothesis testing method. So the null and alternative hypotheses should be formulated such that one contains the claim and the other reflects the opposite position. Since in this example the claim that the average wait time is less than 15 minutes does not contain an equality, we'll set mu less than 15, the claim should be the alternative hypothesis. So in cases like this where the claim corresponds to the alternative hypothesis, the burden of proof is on the claim. If the sample mean is substantially less than 15 minutes, the null hypothesis would be rejected and the alternative hypothesis, or the claim, would be, for lack of a better term, accepted. Otherwise, the null hypothesis would not be rejected and the claim would not be accepted. Because of potential for extreme sampling error, two possible errors can occur when a hypothesis is tested. We have type 1 and type 2 errors. So the errors show the relationship between what actually exists, a state of nature, and the decision made based on the sample information. As you can see, there's three possible outcomes. No error, we made the correct decision. We have a type 1 error or type 2 error. So only one of these will be the outcome for a hypothesis test. Many statisticians argue that you should never use the phrase accept the null hypothesis. Instead, you should use do not reject the null hypothesis. The only two hypothesis testing decisions would be reject the null or do not reject the null. So this is why the jury verdict to acquit a defendant, the verdict is not guilty rather than innocent. The objective of a hypothesis test is to use the sample information to decide whether to reject the null hypothesis about a population parameter. So to perform the hypothesis test, we need to select a cutoff point that is the demarcation line between rejecting and not rejecting the null hypothesis. Recall from the central limit theorem that for large samples, the distribution of the possible sample means is approximately normal, with the center at the population mean mu. The null hypothesis in our example is mu less than or equal to 25 days. So this figure shows the sampling distribution for x bar, assuming that mu equals 25. The shaded region on the right is called the rejection region, and the area in the rejection region gives the probability of getting an x bar larger than the cutoff when mu is really 25. So it is the probability of making a type 1 statistical error. This probability is called the significance level of the test and is given by the symbol alpha. After having chosen a significance level, the decision maker then must calculate the corresponding cutoff point, which is called the critical value. The decision maker carrying out the test specifies the significance level alpha, so you make the decision. The value of alpha is determined based on the costs involved in committing a type 1 error. If making a type 1 error is costly, then we'll want the probability of a type 1 error to be small. If a type 1 error is less costly, then we can allow for a little bit more flexibility and allow a higher probability of a type 1 error. However, when determining alpha, we must also take into account the probability of making a type 2 error, which is given by the symbol beta. Two error probabilities, alpha and beta, are inversely related. So if we reduce alpha, then beta increases. But you have to consider both sides of the issue. So when conducting a hypothesis test, we can use three equivalent approaches. You can calculate a z-value and compare it to a critical value. You can calculate the sample mean x bar and compare it to a critical value. And finally, you can use the more popular method, which is the p-value approach. It really makes no difference at all which approach you use. They all yield the same conclusion. To calculate critical values corresponding to a chosen alpha, we need to know the sampling distribution of the sample mean x bar. So if our sampling conditions satisfy the central limit theorem requirements, or if the population mean is normally distributed, and we know the population standard deviation sigma, then the sampling distribution of x bar is normally distributed with an average equal to population mean mu and a standard deviation sigma divided by square root n. So with this information, we can calculate the critical z value or critical x value, and we compute it the same way that we computed our intervals in chapter 8. So we'll start with our mu and then plus our critical z times sigma over square root n. In essence, this looks like the population mean mu plus our margin of error. So hypothesis tests are formulated as either one-tailed test or two-tailed test, depending on how the null and alternative hypotheses are presented. If a hypothesis test is one-tailed, the entire rejection region is located in the upper tail, and the null hypothesis will be rejected only when a sample mean falls in the extreme upper tail of the sampling distribution. If the hypothesis test is two-tailed, the null hypothesis will be rejected if the sample mean is extremely large on the upper tail or extremely small on the lower tail. The alpha level will be split evenly between the two tails if it's a two-tailed test. So here you can see the three possible variations in hypothesis testing. So on the far left we see a two-tailed test. Mu is equal to c for the null hypothesis, and the alternative, mu is not equal to c. So we have an upper and a lower region where alpha is split between two regions. So in this case, if we computed a z-score that fell below the negative z alpha over 2 or above in a z alpha over 2, we would reject the null. The middle example, we have a lower tail test. So if the null hypothesis is formulated as mu is greater than or equal to some value c, and the alternative is that mu is less than c. So we're going to test that, and if we get a p-value smaller than alpha or a z less than negative z sub alpha, we would reject the null. And then if we had an upper tail test, simply the converse of what we just said for a lower tail test. So here we have an example where research physicians have developed a knee replacement surgery, and they believe it will reduce the average patient recovery time. So the standard procedure is 142 days with a standard deviation of 15 days. So our status quo in this case is that the new method is no better than the original. So we would set our null mu greater than or equal to 142 days, and we'll test our alternative such that mu is less than 142 days. So alpha here is 0.05, so that'll be the lower tail of 0.05, n is 36, x bar is 140.2, and our critical z is negative 1.645. So if we get a z-score less than negative 1.645, we will reject the null hypothesis. So to do this, we'll construct the region, draw it out on a curve, compute our standard error, which is our sigma, 15 divided by square root 36, and set our lower tail alpha at 0.05, and compute our z-score. So it's the statistic minus the parameter over our standard error for the sample, and the corresponding z-score is negative 0.72. So since negative 0.72 is not less than, or does not fall in the rejection region, we will not reject the null hypothesis. So we would say that there is not sufficient evidence to conclude that the new knee replacement procedure results in a shorter average recovery period. So you probably just overpaid. Here's another example. So here we're producing plywood with a mean thickness of 3/8 inch with a standard deviation of 0.05 inch. So here managers want to know whether they're meeting the requirements of that thickness, and they selected a sample of 100 sheets of plywood. So here we have a two-tailed test, so we can either be too thick or too thin on the plywood. And so mu, for the null hypothesis, mu will equal 0.375. That is our status quo. We will reject that if we can prove or have sufficient evidence that we're either too thick or too thin. So we'll split alpha over 2 for our z-score, and if we have a z-score that falls outside of our region, in a rejection region, we will reject that. So here we'll construct the region. Take note that if we split alpha in 2, so 0.05 will be spread over the two regions, the upper and lower tail, that will result in 0.475 for the inner region on each half. Again, we'll compute the test statistic, so statistic minus the parameter divided by standard error. The z-score comes out to be 0.60. And since 0.60 is greater than negative 1.96 and less than 1.96, it's in our lightly shaded blue region, our do not reject region. We will not reject the null hypothesis and conclude that there's not sufficient evidence to reject the null hypothesis. So based on this data, we're meeting the standards. So in addition to the two hypothesis testing approaches we just discussed, a third approach we could do is called the p-value approach. We'd use this instead of the critical value. So if the calculated p-value is smaller than the probability in the rejection region, such as alpha, then the null hypothesis is rejected. If the calculated p-value is greater than or equal to alpha, then the hypothesis will not be rejected. The p-value approach is really the most popular today because p-values are usually computed easily by statistical software packages, including Excel. The advantage to reporting test results using a p-value is that it provides more information than simply stating whether the null hypothesis is rejected. So we can really say that there's a degree of significance of the result. And this allows the reader the opportunity to evaluate the extent to which the data disagree with the null hypothesis, not just whether they disagree or not. So in this example, we've got a company that packages salted and unsalted peanuts in 16-ounce sacks, and we want to test the status quo with the mean fill weight of 16 ounces. So if we fall outside that range, such that alpha equals 0.10, we would reject the null hypothesis. So here we could use the norm.s.dist function in Excel for a z-score of 3.32 to come up with a probability of 0.9995. 1 minus the probability that we found equals 0.0005. And since there's two tails, we'll multiply that by 2. So the resultant would be 0.0010, which is less than our alpha of 0.10. You can also see that it's not just a little less, it's significantly less. So it gives you that measure of extent to which the data disagree. So here we would reject the null hypothesis. So also remember in Chapter 8 we introduced situations in which the objective was to estimate a population mean when the population standard deviation was not known. In those cases, the critical value is a t-value from the t-distribution rather than a z-value from the standard normal distribution. So the same logic applies in hypothesis testing when sigma is unknown, which usually is the case in reality. So this equation would be used to compute the test statistic for testing hypotheses about a population mean when the population standard deviation is unknown. So simply think, if we know sigma, we'll use a z. If we don't, we'll use a t. To employ the t-distribution, we must make the assumption that the population is normally distributed, and if the population from which a simple random sample is selected is approximately normal, the t-test statistic computed will be distributed according to a t-distribution with n minus 1 degrees of freedom. So here we have a tire company conducting a test on new tires. We talked about this earlier, so the mean tire mileage would exceed 60,000 miles. That's what they're claiming. So they took a simple random sample of 100 tires and tested those. X bar came out to be 60.17 and a sample standard deviation of 4.701. Alpha is set at 0.05, and with n at 100, that means our degrees of freedom is 99. So you can go to the table or use Excel to calculate a t critical at an alpha of 0.05 equal to 1.6604. So let's compute a test statistic by taking x bar minus mu divided by s over square root n. So the resulting t that we calculate is 0.3616, which is quite a bit less than our critical t at alpha 0.05. So we wouldn't reject on that basis. We could also compute a p-value. The p-value is 0.3592, which is greater than alpha of 0.05. So just know that a greater region under the curve corresponds to a test statistic that's closer to the center than alpha. So in either case, we're not going to reject the null hypothesis. Alright, so go ahead and open Excel file drug expenses and answer the following question. So in this case, it was reported that average out-of-pocket medical expenses for prescription drugs for privately insured adults with incomes over 200% of the poverty level was $173 in 2002. So we'll use that to formulate our null and alternative hypotheses. So here our null hypothesis will be that the mean is greater than or equal to $173, and that the alternative we're going to test is that the mean is less than $173 out of pocket. So here we'll find a t-critical value such that alpha is 0.01, so that'll be the lower tail since we're testing less than 173. And degrees of freedom will be 196 minus 1. So using Excel, we get a t-critical value of negative 2.35. So any t-calc, we'll call it a t-calculated value, less than that, we will reject the null. So we calculate that by taking x bar minus mu divided by s over square root n. So because we calculated a t-value based on our sample data less than 2.35, we will reject a null and conclude that the 2012 average out-of-pocket prescription drug expenses are actually indeed lower than the 2002 average. We can also find the p-value by either using the table or using our t.dist and using our t-calc and degrees of freedom to find our cumulative probability, resulting in 0.0039. The alternative method that I would recommend is using pH-stat. Here in this case we have a one sample test. We do not know sigma, so we'll use a t-test for the mean, sigma unknown. Our null hypothesis is 173. Level of significance, alpha is 0.01. We know the sample size is 196. The sample mean is our x bar of 167.52. And S, or the sample standard deviation, is 28.52. This is a lower tailed test. When you click OK, it will give us our output. So here we see our standard error. Degrees of freedom is n minus 1, so 196 minus 1, and our test statistic that we calculated earlier. Here's our lower critical value, so we would say that this falls in the range of our rejection region, so we reject based on that. We also have a p-value that is less than our alpha, or level of significance. I think the easiest way to handle this chapter is to understand how to set up the hypothesis, the null and alternative, and then use pH-stat to do the computations for you. Alright, thanks for tuning in this long. That wraps up Chapter 9, Section 1.